Have you ever wondered how your smartphone can recognize your face to unlock itself? Or how it can instantly translate a foreign language you see on a sign? This isn't magic, even though it certainly feels like it. This incredible technology is powered by something called a neural network. It's a type of artificial intelligence that is becoming more and more a part of our daily lives, working silently in the background to make our devices smarter and our lives easier. You might not see it, but it's there when you search for photos of your cat, and your phone knows which ones to show you. This guide will pull back the curtain on this amazing technology and show you that it's something you can understand and even build yourself. A neural network is a computer system designed to work a bit like the human brain. Our brains are made of billions of tiny cells called neurons. These neurons are all connected, sending signals to one another to help us think, learn, and make decisions. A neural network in a computer does something very similar. It has its own version of neurons, called artificial neurons, which are connected in layers. Just like we learn from experience, a neural network learns by looking at examples. It tries to find patterns in information, whether that's recognizing a face, understanding words, or even learning to play a game. The idea is to mimic the way our own minds learn, creating a powerful tool for solving complex problems. The comparison to the human brain is a very helpful way to start. Think about how a child learns to recognize a dog. They see many different dogs, big ones, small ones, fluffy ones, and short-haired ones. Each time they see one, their brain adjusts its understanding of what a dog is. A neural network learns in much the same way. You show it thousands of pictures of dogs, and it slowly learns the features that make a dog a dog. It learns about floppy ears, wagging tails, and wet noses. It isn't programmed with rules like if it has 4 legs and fur, it's a dog. Instead, it discovers these patterns on its own, which is what makes this technology so powerful and flexible. This guide is your first step into this exciting world. We will break down everything you need to know into simple, easy to understand pieces. You do not need to be a math genius or a computer science expert to follow along. We will start with the very basics, explaining what you need and how to set it up. Then, we will build a simple neural network together, one that can learn to tell the difference between two numbers. By the end, you will not only understand how neural networks work, but you will have the confidence to continue exploring and building more complex things. So let's begin this journey and unlock the secrets behind the magic in our technology. Before we can start building our neural network, we need to gather a few simple tools. Don't worry, these tools are free and easy to get. The main tool we will use is a programming language called Python. Python is one of the most popular languages in the world for artificial intelligence because it is very easy to read and write. Its commands look a lot like plain English, which makes it perfect for beginners. Many computers already have Python installed, but if yours doesn't, you can download it easily from its official website. Think of Python as the language we will use to speak to the computer and give it instructions on how to build and train our network. The second tool we need is a special library for Python called NumPy. A library is like a toolkit that gives a programming language extra powers. NumPy is short for numerical Python, and it is excellent at working with numbers, especially large groups of them. Neural networks do a lot of calculations with numbers, and NumPy makes these calculations very fast and very easy to write. Instead of having to write many lines of code to perform a mathematical operation, NumPy often lets us do it in just one line. It helps us organize our data into special lists called arrays, which are perfect for feeding information into our network. Installing NumPy is also simple, usually requiring just a single command in your computer's terminal. So to recap, our workshop has two main tools: Python, our friendly and readable programming language, and NumPy, our powerful toolkit for handling all the numbers. To set them up, you will first need to install Python. Just go to the python.org website and follow the download instructions for your computer, whether it's a Windows PC, a Mac, or a Linux machine. After Python is installed, you can open your computer's command line or terminal. From there, you will type a simple command like pip install numpy. The pip tool is Python's package installer, and it will automatically find, download, and install the numpy library for you. It's like an app store for Python tools. Once you have both Python and numpy ready, you are all set to start your journey. You don't need any other complicated software or expensive hardware to begin. A standard laptop or desktop computer is more than enough for building your first simple neural network. The beauty of this field is how accessible it has become. With just these two free tools, you have everything the professionals use for many of their projects. Now that our digital workbench is prepared, we can move on to the next important step: finding and preparing the data that our neural network will learn from. This is where the real fun begins, as we start to think like a teacher preparing a lesson for a new student. Every neural network needs a teacher, and that teacher is data. A network learns by looking at examples, so we need to provide it with good, clear examples to learn from. For our first project, we will teach our network a very simple task: how to distinguish between the numbers 0 and 1. This is a classic starting point because it's easy to understand. Imagine we have images of handwritten zeros and ones. Our goal is to train the network so that when we show it a new image of a 0 or a 1, it can correctly identify which number it is. The first step in this process is to collect and prepare this data so the computer can understand it. Computers don't see images the way we do. They see a grid of numbers. Each number in the grid represents the color or brightness of a single tiny dot or pixel. For a simple black and white image, we can use a 0 to represent a white pixel and a 1 to represent a black pixel. So, a handwritten 1 might be represented by a grid of numbers with a line of ones in the middle, and a handwritten 0 might be a circle of ones. We need to turn our images into these numerical grids. This process is called data preparation, and it's a crucial step. The quality of our data directly impacts how well our network can learn. Garbage in, garbage out, as the old saying goes. Let's imagine our images are very small, perhaps a grid of 3 by 3 pixels. A simple one might look like a column of ones, and a 0 might be a square of ones with an empty middle. We would create a set of these examples for our network to train on. This is called our training set. For each example in our training set, we also need to provide the correct answer or label. So for each grid of numbers that represents a 1, we would attach the label 1. For each grid that represents a 0, we would attach the label 0. This way the network can check its own work. It makes a guess, compares its guess to the correct label, and learns from its mistakes. Gathering and labeling data is one of the most important jobs in all of artificial intelligence. For our simple example, we can create this data ourselves. But for real-world problems, like identifying cat photos, scientists use huge data sets with millions of labeled images. For now, we will stick with our simple numbers. We will create a handful of examples for zeros and a handful for ones. By preparing our data carefully, we are setting our neural network up for success. We are giving it a clear textbook with plenty of examples and all the correct answers in the back. Now that our data is ready, we can start building the structure of our network. Now that we have our data, let's talk about what our neural network is actually made of. The most basic part of a network is the artificial neuron, sometimes called a node. Just like a brain cell, an artificial neuron receives signals, does a little bit of thinking, and then sends a signal of its own. A single neuron is a very simple thing. It takes in one or more inputs, which are just numbers. For our example, the inputs would be the pixel values from our image grid. If our image is a 3 by 3 grid, that's 9 pixels, so our first neurons would each receive 9 inputs. The neuron then processes these inputs and produces a single output, which is another number. How does a neuron decide what to output? This is where a very important concept comes in: weights. Each input that comes into a neuron has a weight associated with it. A weight is just a number that tells the neuron how important that input is. If a weight is a large positive number, it means that this input is very important for making the neuron fire. If the weight is a small number or a negative number, it means the input is not very important, or it might even prevent the neuron from firing. The neuron takes all its inputs, multiplies each one by its corresponding weight, and then adds them all up. This sum is the neuron's initial thought, but it's not the final output just yet. This idea of weights is the absolute key to learning. At the very beginning, when we first create our network, we don't know what the weights should be, so we just assign random numbers to them. This means our brand new network is like a newborn baby. It doesn't know anything and will make a lot of mistakes. The entire process of training the network is about slowly and carefully adjusting these weights. The network looks at a training example, makes a guess, and then checks the correct answer. If its guess was wrong, it goes back and adjusts the weights slightly, so that next time it is more likely to get the right answer. This is how learning happens. Of course, a single neuron isn't very powerful on its own. The real power comes from connecting many neurons together in layers. A A simple neural network has at least three types of layers. First, there is the input layer. This layer doesn't do any thinking, it just receives the initial data. For our 3x3 pixel image, the input layer would have 9 neurons, one for each pixel. Next, we have one or more hidden layers. This is where the real processing happens. The neurons in the hidden layers receive signals from the input layer and pass signals to each other. Finally, there is the output layer. This layer gives us the final answer. For our task of distinguishing zeros from ones, our output layer might have just one neuron, which will output a number close to 0 or close to 1. So, we mentioned that a neuron takes its inputs, multiplies them by weights, and adds them up. But there is one final crucial step before it produces its output. This step is controlled by something called an activation function. An activation function is basically a simple mathematical rule that decides whether a neuron should fire or not, and how strongly it should fire. It takes the summed up signal from the neuron and, well, squashes it into a more useful format. Think of it, like a light dimmer switch. The summed signal is the total power available, but the dimmer switch, the activation function, decides how bright the light should actually be, from completely off to fully on. Now, one of the most common and easy to understand activation functions is the sigmoid function. All it does is take any number you give it and transform it into a value between 0 and 1. If the input number, the sum of weighted inputs, is very large and positive, the sigmoid function will output a number very close to 1. If the input number is very large and negative, it will output a number very close to 0. If the input is exactly 0, it outputs 0.5. This is incredibly useful because it turns the neuron's internal calculation into a neat, predictable output. For our output neuron, this is perfect. An output close to 1 could mean I'm very confident this is a 1, while an output close to 0 could mean I'm very confident this is a 0. Let's use an everyday analogy to make this even clearer. Imagine you are deciding whether to bring an umbrella with you when you leave the house. You consider several factors or inputs. Is the sky cloudy? Does the weather forecast predict rain? Is your friend with an umbrella waiting outside? You might give each factor a different importance or weight. A dark, cloudy sky is a very important factor, so it gets a high weight. Your friend waiting is less important, so it gets a low weight. You add all these factors up in your mind. The activation function is your final decision-making process. If the combined factors strongly suggest rain, you activate and decide to take the umbrella. If not, you don't. The activation function turns a messy combination of factors into a clear yes or no decision. There are many other types of activation functions besides sigmoid, each with its own strengths, but the core idea is the same. They introduce a non-linear, decision-making element to the network. Without them, a neural network would just be a very complicated linear equation, and it wouldn't be able to learn complex patterns. It's this simple step, repeated across many neurons, that gives the network its power to model sophisticated relationships in data. It's what allows the network to draw curved, complex lines to separate different categories, instead of just straight lines. This little spark of decision is what makes the network intelligent. Now, let's see how all these parts work together to process information. Now, we have all the pieces in place. Our data, our neurons, our weights, our layers, and our activation functions. It's time to see how they all work together. The process of passing information through the network to get an answer is called forward propagation. It's called this because the information moves forward from the input layer through the hidden layers to the output layer. Let's walk through it step by step with our number recognizing network. First, we take one training example, say an image of a handwritten 1. We flatten our 3x3 pixel grid into a simple list of 9 numbers and feed these numbers into the 9 neurons of our input layer. Each neuron in the input layer then passes its value to every neuron in the first hidden layer. As the values travel along these connections, they are multiplied by their corresponding weights. Each neuron in the hidden layer receives 9 signals, one from each input neuron, multiplies each by its weight, and sums them all up. After this sum is calculated, the neuron applies its activation function, like the sigmoid function, to this sum. The result is the neuron's output, a single number between 0 and 1. This process is repeated for every single neuron in the hidden layer. They're all doing their own little calculations at the same time. The outputs from the first hidden layer now become the inputs for the next layer. If we have more hidden layers, the process repeats. The signals flow forward, getting multiplied by weights, summed up, and passed through activation functions at each layer. Finally, the signals reach the output layer. In our simple case, we have one neuron in our output layer. It takes the outputs from all the neurons in the last hidden layer, multiplies them by their weights, sums them up, and applies its activation function one last time. The final number that comes out of this output neuron is the network's prediction. For our image of a 1, we hope this number is close to 1. But what happens at the beginning when all the weights are random? The network's prediction will also be random. We might feed it an image of a 1, but the output could be 0.3, which is not very close to the correct answer. This is where the learning really starts. We need to measure how wrong the network's answer is. We do this by calculating the error. The error is simply the difference between the correct answer, the target, which is 1.0, and the network's predicted answer, the actual output, which was 0.3. In this case, the error is 1.0 minus 0.3, which equals 0.7. A large error tells us that the network is very wrong. A small error means it's getting close to the right answer. Our goal during training is to make this error as small as possible. Once we have calculated the error, we need to use it to fix the network. We can't just tell the network it was wrong, we need to show it how to get better. This is done using a clever process called backpropagation. As the name suggests, it's the opposite of forward propagation. Instead of information flowing forward, the error signal flows backward through the network, from the output layer to the input layer. The purpose of backpropagation is to figure out which weights in the network were most responsible for the error and then adjust them accordingly. It's kind of like a manager walking back through the assembly line to see which station made the mistake. The process starts at the output layer. We look at the error, the difference between the desired output and the actual output, and use a bit of calculus to determine how much the weights connected to the output neuron contributed to that error. The weights that had a bigger impact on the final sum will be considered more responsible. We then adjust these weights slightly. If the network's output was too low, we might increase the weights that would have made it higher. If the output was too high, we might decrease them. We only make a very small change each time because changing one weight can affect the entire network's behavior. After adjusting the weights for the output layer, we continue moving backward to the last hidden layer. The neurons in this layer didn't produce the final error directly, but they contributed to it by sending signals to the output layer. We can calculate how much each hidden neuron contributed to the final error, and then, just like before, we adjust the weights connecting to that hidden layer. This process continues layer by layer, moving backward all the way to the first hidden layer. We are propagating the error signal back through the network and using it to fine-tune every single weight along the way. This is the heart of how a neural network learns. This entire cycle, forward propagation to get a prediction, calculating the error, and back propagation to adjust the weights, is done for a single training example. To train the network properly, we must repeat this cycle over and over again for every example in our training set. And we don't just go through the training set once, we go through it many times. Each full pass through the entire training set is called an epoch. A network might need to be trained for hundreds or even thousands of epochs. With each epoch, the weights are adjusted little by little, and the network's overall error should gradually decrease. This is a slow and patient process, like sculpting a statue from a block of stone, with each adjustment bringing it closer to the final form. Sometimes you might find that your neural network isn't learning. You run it for many epochs, but the error rate doesn't go down, or it jumps around randomly. This is a common problem, and it's a normal part of the learning process for you as a developer. The first thing to check is your data. Is it clean and correctly labeled? Even a few incorrect labels can confuse the network. Also, make sure you have enough data. If you only show the network one or two examples of a 0, it might not be able to learn the general pattern. You should also check if your data is properly normalized, meaning the numbers are scaled to a consistent range like 0 to 1, which we did by representing pixels this way. Another common issue is the learning rate. The learning rate is a small number that controls how much we adjust the weights during backpropagation. If the learning rate is too high, we might be adjusting the weights too drastically. Imagine you are trying to tune a radio. If you turn the knob too quickly, you will overshoot the station. This is what a high learning rate does. The error might jump around and never settle down. If the learning rate is too low, the training will be very, very slow. It's like turning the radio knob incredibly slowly. You'll get there eventually, but it will take a long time. Finding the right learning rate is often a matter of experimentation. If your data and learning rate seem fine, you can look at the architecture of your network itself. Maybe your network is too simple for the problem. A network with only one very small hidden layer might not have enough brain power to learn a complex pattern. You can try improving it by adding more neurons to the hidden layer, or by adding more hidden layers. This creates a deeper network, which can learn more intricate and abstract features from the data. However, be careful not to make the network too complex, as this can lead to a problem called overfitting, where the network memorizes the training data but can't generalize to new unseen data. Finally, you can experiment with different activation functions. While sigmoid is great for beginners, other functions like RealU, rectified linear unit, are often more effective for hidden layers and deep networks. Don't be afraid to try different things. Building neural networks is part science and part art. It involves a lot of experimentation, observation, and intuition. Every time you troubleshoot a problem, you are learning more about how these fascinating systems work. The key is to be patient, change one thing at a time, and observe the effect it has on your network's performance. What we have built is a simple but complete neural network. This same fundamental structure is the basis for the incredible AI you see in the world around you. When you use a translation app, a deep neural network is at work, one that has been trained on millions of sentences in different languages. When a self-driving car identifies a stop sign, it is using a complex neural network that has been trained on countless hours of driving data. Facial recognition, medical image analysis, and the recommendation engines that suggest movies or products to you, all of these are powered by neural networks, just much larger and more complex than our little number recognizer. The great news is that artificial intelligence is for everyone. You do not need a PhD or access to a supercomputer to get started. With a curious mind and a willingness to learn, you can explore this field. Start small, just like we did in this guide. Celebrate your successes, like making your first network correctly identify a number. Don't be discouraged by errors. They are your best teachers. The AI community is incredibly open and collaborative, with endless resources available online. There are tutorials, free books, and forums where people are always willing to help beginners. You are not alone on this journey. Here is a simple plan to continue your learning. First, really master the basics we've covered. Try to build the number recognizer yourself from scratch. Then challenge yourself by expanding it to recognize all digits from 0 to 9. Next, explore popular AI libraries like TensorFlow or PyTorch. These tools make building complex networks much easier. You can then move on to classic beginner projects like a network that can classify different types of flowers or one that can identify spam emails. Each project will build your skills and your confidence, opening up new possibilities. A few golden tips for your journey. Be patient and persistent. Learning AI is a marathon, not a sprint. Some concepts will be tricky, but if you stick with them, they will eventually click. Find a community. Join online forums or local meetups. Learning with others is more fun and can help you overcome challenges faster. Most importantly, stay curious. The field of AI is constantly evolving, with new discoveries being made all the time. By building your first neural network, you have taken a step into a larger world. You have learned the language of modern technology and opened the door to a future where you can be a creator, not just a consumer. The future of AI is bright, and it's a future you can now help build.